Okay, so I'll get started. So I welcome the viewers to this problem solving and live interaction session for the subject engineering mechanics offered by Professor K. Ramesh in the SWAYAM portal. So today we will be looking at problems from week 9, which has to do with relative motion analysis of velocities and accelerations. Okay, so let us look at the first problem. An observer sits at point B. So this is point B. So we have point B over here. So the observer sits at point B and observes the peg P moving along the slot while rotating with the slotted plate. So the observer is sitting at point B and he is rotating with this plate while observing the peg P. Which of the following quantities cannot be measured by the observer in this case? Is what is asked. So, so the options say it is relative velocity of the peg P, tangential component of the acceleration of peg P, the normal component of the relative acceleration of peg P. The previous option also says relative acceleration, and the last is Coriolis component of the acceleration of the peg P. So while rotating with the reference with the rigid object, naturally all the relative quantities can be measured by the observer. The only thing that cannot be measured is the Coriolis component of the acceleration of this peg P, which is by virtue of this rotation itself. So when an observer is actually rotating with this rigid object, the observer will also have that the angular velocity of that rigid object. And Coriolis component, we know it is 2 omega of that rigid object cross VREL. VREL will be along the slot. But omega, since the observer is also rotating, so the observer will not be able to make that assessment. Hence, Coriolis component cannot be measured, which is why this is actually a non-inertial reference frame. So in order to make this inertial, it needs a correction, which is the Coriolis component. That needs to be added to the acceleration evaluation made by the person rotating with the frame. Okay. So let us look at this question. Give midway, if you have any questions or doubts, you please feel free to stop me and ask. In the meantime, I'll move forward. So given that the block A, so we have a block A here. We have one block A which is confined to slide in a horizontal slot, and the link BC, essentially this is the crank. It is vertical at the instant shown is what is given. So this is 90 degrees. Is what is given. It can be concluded that the link AB is undergoing pure translation at this instant. So let us see whether this is true or not. So if I were to take this, now I know that the velocity of point B, by virtue of this being at 90 degrees, with that, if this is having some omega, then naturally velocity of point B will be pointing like that. So let us say that I take my axis like that. Let us say this is X. Yeah, so let us say this is X and this is Y. So VB, the vector, will actually be some VB, its magnitude I cap. So this much we know. Another thing we know is that VA, let the velocity of A be given by that. So this is VA vector. Another thing we know is that VA is nothing but that is also horizontal by virtue of that being confined to that slot. So from relative motion analysis, let me remove this. From relative motion analysis, if I were to take this non-rotating translating axis and attach it to A, Let me put it in black and then attach it to A. Now, let us say that this connecting rod AB is having an omega AB. We are just assuming it to exist, and then we will see whether it actually exists or not. So we know that velocity of B with respect to this axis, now it can be written as velocity of A plus omega of AB crossed with RB with respect to A, where RB with respect to A is the position vector of B with respect to A. Omega, we are assuming it to exist. Now let this angle be some theta. Let us take this angle to be some theta. So RB with respect to A, we can write this as, let us say the length of AB is unity. Let us assume it to be 1 meter for now, for ease of calculation. So this will come out to be cos theta I cap plus sin theta j cap. Why? Because this is the vector that I want to represent. So this is I cap and this is j cap, cos theta j cap. And since the magnitude is 1, I needn't multiply it. Okay. So if I represent this in component form now, representing this in component form, I know VB is nothing but having only one component as I cap. Similarly, VA I cap plus omega AB. Let us assume that it is rotating like that in the along the positive k cap, crossed with this vector. Crossed with this vector. So if I were to cross multiply this, so this gives me omega I cap. It's nothing but is VB I cap is equal to VA I cap minus sin theta omega AB I plus cos theta omega AB J. I have just opened it out, done nothing else. So now if I take this again and I group the I and j terms, so I have this coming in 1. Let me write it like that. So it is VA minus sin omega AB I plus something j. So if we have to separate out I and j components, this implies that VB is nothing but VA, VA minus omega AB sin theta. And the other equation we get is 0 is equal to omega AB cos theta. Because there is no j component on the left hand side. So we have only 0. So for this configuration, we can clearly see that theta is non-zero. And it is lying in the positive quadrant. It is not 90 degrees. So cos theta cannot be 0. This in fact implies that omega AB is actually 0. Omega AB therefore is 0. And substituting this here, we get VB is nothing but VA. So we are having a link like that, which is having a velocity here, which is VB, and then it is having the same velocity here because VA equal to VB, and it is having no rotation. So at this instant, it can be concluded that it is indeed undergoing pure translation. But at the very next instant, it will have some rotation as well. So it will be undergoing general plane motion. So this is actually one of the extreme conditions that happens. Why this is happening is, in the previous step, it would have been something like that. Now it came here, it stopped, and in the next instance, it will go back. So essentially, this is the point where omega shows a reversal. That is why this is having a pure translation at this instant by virtue of this. Another way to look at this, we can quickly gauge, is that let us say I have the bar like that. I know this is VB and I know this is VA. Now this bar is rigid. Since we are dealing with rigid body mechanics, this bar is definitely rigid. We have seen, we have taken this angle to be theta. So from here, what will be the component of velocity along this direction? So this will be nothing but VA cos theta. Similarly, if I were to take this point and then resolve the component of VB along this direction, this will be nothing but VB cos theta. This is also theta by virtue of A and VB and VA being parallel. Now, if this is a rigid object, then definitely VB cos theta needs to be equal to VA cos theta. If this is violated, then the rigid body, then the very idealization of the rigid body is violated, which shouldn't be the case. So from here, it follows that VB is equal to VA. This is a quicker way to do it, that VB is equal to VA. Otherwise, we can always go by first principles like we did. We attached non-rotating translating axis at A. Using relative motion analysis, we assumed one omega to exist. We solved for it, and then we found towards the end that this was actually coming out to be 0. So I take it that this is clear. Yeah, yeah, yes, yes. But if I were to quick, yes, yes, please go ahead. No, essentially for any rigid body, when we take 2 points, the line joining that point, the velocity along that line has to hold, has to be equal. Otherwise, it violates the condition for rigid body. So this will always hold. The only thing is when we take a general rigid body, let us say, if I were to take a general rigid body of this form, and then I have one velocity at this point like that, and the other velocity something like that. Now, what happens is if I were to join these two by a line, and let us say I extend this. Now, this will be one angle. This will be one angle which I have to evaluate. This will be the other angle which I have to evaluate. In which case, we saw here cos theta was the common thing that got cancelled out, which will not happen there. By virtue of which VB will not be equal to VA. That will be the difference. A special case of this is when these two angles are same, by virtue of that being parallel. In such a case, definitely this will hold. I hope that I've answered. No, it will not be same. In fact, it will have a linear variation like this. See, for B, yeah. Let us say that we started not from BC, instead we started from A. I think I got your question. I'll just try to explain it. Let us say we have fixed at A and then we are given omega AB to exist somehow. In such a case, we will get at some other configuration, we will get VB. From that, now if we were to analyze from this, in this very specific case, our velocities are going like that. So at some other point in BC, the velocity is linearly reducing to 0. So you can apply similar triangles and find out, but it won't be same. It is essentially undergoing fixed axis rotation. VB, exactly. We need to find out only velocity VB. Then we need to do this, resolve it along this direction. But mind you, we resolved along this and then found that this angle is also theta by virtue of knowing that both the velocities were parallel. If you know that both the velocities are parallel, then definitely only VB you need to find. VA automatically takes care of itself. Yeah, for this specific arrangement, at the next instant, when we take the crank will be something like that, and the connecting rod will be something like that. In such a case, VB will be like that. But VA still is parallel. These two are not parallel. You understand the point? Yeah, yes, yes. In that case, you need to know the different thetas, but if you know those different thetas, you can definitely find that out. Yeah, but it will involve some geometry. In such a case, it will involve some geometry, but other than that, you can definitely find that out. Shouldn't be a problem. For a configuration that is not this way. Okay. Yeah. Yes. By virtue, see, that is generally done by virtue of taking one to be rigid only. So we find relations for one point with respect to one atom, and then for the other point, the other quantities that we want to relate. What we eventually do is these two should move, these two velocities at the ends of that link has to be same. By that way, whatever quantities you evaluated to get VA and whatever quantities you had to get to VB, those two get related by this constraint that AB is rigid. So if you solve a handful of problems there and then you have specific questions, then you can like maybe ask. Because in general, I'm saying how this will go about. And in this specific case, we have these two angles to be same. So by virtue of that being same, our velocity quantities also come out to be same. If this was not the case, let us say if this was at the next instance, it was like this, then in that case, it is no longer parallel, but nonetheless, if we know this angle, then we can find it out. But to know that angle, you have to do some geometry. Rather, if you go by this first principles, our vector analysis, that also can give you the answer. Now, I'm not sure if I've answered you. If I've not, you please raise the specific question. I'll try to address it. Okay, right. Thank you. Okay, so let us move on to the next question. So the question says, in order to solve for the kinematical quantities for the bar AB and the rod BC and the rod DE, there are two rods, using the concept of coincident points, which of the following statement should hold is what is asked. The fictitious points or the point which we take over the actual point of interest should be taken on the bar AB at C, should be taken on the rod DE at C, and then we have other two questions, which is the absolute velocity of point C would be perpendicular to bar AB, the absolute velocity of point C would be perpendicular to rod DE. So this is the question. So let us try to look at this. Now we have a bar like that, and then we have another rod like that. Both are pivoted at the ends, so both can undergo only fixed axis rotation. And then we have one collar like that, and then I have a pin. So let me take this here. Okay, first let us look at this section. So the collar is like that. Very well. Now I can see that if I remove this bar like that, I have, and I separate it out, I have one system of AB with a pin which is attached to a collar, and then I have this rod. I have dismantled it just conceptually. Now, in such a case, I have this pin here and this pin here. This is point D and this is E. Now, this is point A. This is point A and this is point C. In this case, I know that this this bar has to invariably rotate about A. So it doesn't have any other option because of the constraint given in the question that it is pinned. In such a case, we invariably know what the velocity of this would be. It can either rotate that way or it can rotate that way at best. So we naturally know that the velocity would have to be like that or like that, depending on how it is rotating. In such a case, given the angular velocity of AB, this is B, given the angular velocity of AB, VC is always known. This is VC. So VC is always known. Absolute velocity of VC is always known. Whereas if let us say I take this rod and then I put it through the collar here now. Now I can see that the collar can actually slide over this green rod. So in essence, in order for me to calculate VC with respect to DE, I definitely need to attach the coincident point to or the fictitious point to this green rod, because the other rod is actually having that point. So the rod which doesn't have that point, that is where we fix the fictitious point. So in such a case, it would have to be attached to the rod DE. So far, so good. Now this says the absolute velocity of point C would be perpendicular to rod AB or to rod DE. Now let us look at this in a little more detail, just so it is clear. Now if I take this here and let us say, so this will be kind of the circle that it will trace. I have a circle. Let the circle center be at A and let it trace it like that. Somewhat approximately I'm doing it just to give the idea of what is going on. Let me erase this. So it is, with respect to this, it is traversing this curve. It is tracing this curve. Okay. I'll put it here. Yeah, DE. Yes, yes. From the figure also, if you see, yeah. Yes, slider is okay. You are asking something related to this mechanism, kinematics, but this is having one pin and one prismatic pair, so it will have to be counted. Yeah. Now let us say a, in the next this thing, I take one circle and then I put it through D and let it pass through. Let it have the center at D. Let this be another circle it traces. Okay. Now let us say after time t, sometime I take a point here. I know the velocity of this point would have to be parallel like this. So let me call this point which I have taken, let me call this F. Let us say it is some fictitious point. So I have called it as F. So this is velocity of F after some time. At the same time, my actual point C would have moved here. So that will be having a velocity like that, which is parallel to the circular path. In such a case, this is actual velocity of point C. Now let me take these two vectors separately. I have one vector here and I have the other vector here. Now if I were to place one tip here, both the tips I join and I have one new vector which connects this to this. So what will this be? This will be velocity of point C as observed by as observed by the fictitious point F. So in such a case, what can this give us? The vector equation which it gives us is velocity of C is nothing but velocity of that point plus velocity of, I'm sorry, 1 minute, plus velocity of c with respect to f. Now, in the limiting case, if I take this point, this time instant to be at that very instant, which is shown in the question, I know that my velocity of c with respect to f has to always be parallel to my rod dE. So after some time, at the time at which I have taken, it would be like that. So my velocity would actually be pointing towards d. That is one. So that is actually, it is behaving like a slotted member, you can say. Slotted member or a collar, howsoever it is. So it is actually pointing towards D invariably. So it is parallel to that slot. And the other one, I can see it is perpendicular to that slot. So if I know this vector and it is traveling with, it is rotating with some omega, this omega cross this F will give me Vf. So that is what we essentially are doing. In such a case, once I know Vc vector, the absolute velocity from the actual crank, in such a case, Vf will be omega of that dE crossed with R of F with respect to D plus Vc with respect to F, with the constraint that this will always be parallel to slot. This will always be moving parallel to the slot. So this is the entire concept of coincident points from vector analysis. This is what we try to do. So we will see its application in the subsequent questions. Okay. So let us move on to this question. So we have two disks D1 and D2 attached together. Yeah, yeah. In what? Yes. Yeah, yes. Yes, definitely we need to consider the Coriolis component when we attach the rotating frame of reference to DE. However, this is where velocity analysis as of now. If when we are doing acceleration analysis, we definitely have to account for that. Whereas if we fix our non-rotating translating axis at VA, if we were to set it at VA, in that case, the point C, the collar is actually attached to this. We need not rotate with it. In such a case, you are always in a position to get absolute acceleration of point C. That is not a problem. The only problem is when you analyze it from DE's perspective. In such a case, since it is rotating and we are having a relative motion with relative to that bar, in such a case, we have to account for Coriolis acceleration, which is what is the entire concept of, yeah. We will not be able to perceive Coriolis component watching from DE when we are rotating with DE. So this is a correction we need to make in order to get the absolute acceleration. Let us say that I was rotating with AB. Will I see V move anywhere? But I will not see V move anywhere. There will be no relative motion because I'm rotating with AB. In such a case, its acceleration is known. It is having only centripetal acceleration. If it is rotating with some tangential acceleration, then that will also, with some angular acceleration, that will also get added to its acceleration. Let us say this will have a centripetal acceleration like that, and let us say it is having a tangential acceleration like that. So eventually, the point C's actual absolute acceleration will be something like that in the most general case, either like that or like that, whatever that be the case. Now, when I apply the same an axis with DE and I'm rotating with it, I have to finally match my acceleration to this, which is the absolute acceleration. In such a case, I have to make one correction, which will be the Coriolis component, which I will not perceive when I'm rotating with DE. Is it clear? We'll be feeling it when we look at it from AB. No, I'm asking you the question. See, Coriolis is It only exists when a relative velocity exists. You understand? So if you are rotating with AB, let us say you attach a rotating frame of reference to AB, are you seeing C move somewhere? C is not moving with respect to you because you are rotating with AB and C is pinned to AB. So in such a case, VREL is 0. So there is no Coriolis component in that case. Whereas if you are rotating with DE, you can see because of the virtue of this being a prismatic pair, a slider, it is actually moving. In which case there is non-zero VREL. In which case there will be Coriolis component. Is it clear? Yeah, yeah. Okay. So here we have two disks D1 and D2 which are attached together and are confined between two platforms as shown. At the instant depicted, so we have two disks here which are attached, and at the instant depicted, this platform A moves to the right with a constant velocity while platform B remains stationary, such that the disk rolls over platform B without slipping. So essentially this is rolling over this point, and this platform is the reason why. So answer the following question for the instant depicted is what is asked. Okay, so what are the questions? One is the angular velocity of the disk, the magnitude of the angular velocity of the disk, and then the magnitude of angular acceleration of the disk, the magnitude of absolute velocity of point C on the rim of disk. So we have one point C on that rim. So we need to find out the absolute velocity of that point and the absolute acceleration of that point. So this is what we need to do. Okay, so let us take this. This is one disk we have. And then I have another smaller one like that. And these are fused together as one unit. Now, if I were to take it here, what do I know? That at this point, the velocity is 1.5 meters per second to the right. I know that. That is given. Another thing it says is that the platform B, the disk rolls over platform B without slipping. In such a case, I know that this point is having zero velocity. So if I were to join it like that, this is behaving like the instantaneous center of rotation. In such a case, the variation of angular velocity is like that. The variation of linear velocity is like that by virtue of this rotation. Let us say that I have this omega like that. So omega of the disk assembly, let me just say the disks. Omega of the disks cross r of this point. Let me call this point some p, and let me call this point O. So Rp with respect to O is given to be 1.5 I cap. So I know Rp with respect to O is nothing but the sum of these two. This distance is 0.5, this distance is 0.25. So it is actually 0.75. So in such a case, if since I have been asked only magnitude, I need not go with some big vector analysis. I can simply see that omega disk into 0.75 gives me 1.5. So omega disk is 2 radians per second. And in the vector form, omega disk is, if I take my axes like that, if this is x, this is y, then omega disk is minus 2 k cap. Since the magnitude is asked, I know this is 2 radians per second. Okay, so now next question what is asked is the magnitude of angular acceleration of the disk assembly in radians per second. Now I can see that this is what this says is it is having no, the platform moves to the right with a constant velocity. So there is no change in the velocity, in which case my angular acceleration is 0. So the angular acceleration of the disk assembly is 0. Now that we know this, let us try to look at point C. Now I'll just take these two from here. Maybe add a sheet here. Okay. Yeah. Yes. No, actually it was my mistake. I shouldn't have named this O. Let me call this O prime. O is this point. It is actually rolling without slipping over this point. O is the center of the disk. O dash is not slipping. O dash is the OCR, ICR. Why? Why is that so? Let us say you have a wheel. It is rotating on a floor which is stationary. It is rolling without slipping. Now, is it necessary that the floor has to move? The floor can be stationary and the disk can roll on it without slipping. What is the problem? Yes. This assembly is moving forward to the right. It is rolling by virtue of the movement of platform A, which is over that disk. So it has nothing to do with platform B's movement. Okay, yeah. All right. That's a good question. Okay. So let us look at this point. Now we know that this point is there, and then we know that the assembly's angular velocity is. Let me not write disk time and again. Let me just write this to be 2k minus 2k cap. Okay. All right. Now let us try to look at this point. So this is the position vector of that point. Now the question is asking what is the absolute velocity of point C. Now when I know the ICR, I can even easily calculate what is the absolute velocity. So it will appear like that. My absolute velocity of point C will be perpendicular to that. It will be like that. So what will be the magnitude of this? This is Vc. So magnitude of Vc is nothing but omega of this assembly into this. This is R of C with respect to O prime. With taking note that O prime is the ICR. Right. So this is nothing but into the length of R C with respect to O prime. Now do we know R C with respect to O prime here? In this question, we know this distance is 0.25. We know this distance is 0.5. So simply we can calculate that distance. What will that come out to be? It will be root over. So this will be nothing but 2 into root over 0.25 squared plus 0.5 squared. So the absolute velocity of C, the magnitude, will be 0.25 squared plus 0.5, right? Yeah, 0.5 squared root over into 2. So it comes out as 1.12. Omega of the disk assembly. Ah, yes. By virtue of that being connected to that point, we are taking point C at the rim of that assembly only. So since this is the ICR, all the points will be having velocities perpendicular to their position vectors at this instant. Yes, omega and alpha, no matter how we analyze it, for one rigid body, there can be only one omega. Omega, yeah, we are looking at this instant, right? All these are at some instant. If there is non-zero acceleration, then at some other instant, we will be having O dash would have moved somewhere else. We will label a new point O double dash, and then we will analyze with respect to that. C would have moved here. At this instant is what the question is asking. For this instant depicted. Yeah. Velocity or acceleration? See, O dash is actually the point of zero velocity in this assembly. So its velocity is already zero, but it has non-zero acceleration nonetheless. Is it a question you're asking? Yeah, because see, we are taking 2 points. We are taking a rigid body. We are taking a rigid body, and then we have some velocities. Let me draw this as an ellipse, just to be clear. Okay, this is the rigid body. We know two velocities like that. So what we are trying to do, we are actually trying to connect these with a perpendicular, saying that with respect to this, these are rotating. If it falls within the body, it is having fixed axis rotation about that point. So naturally, the velocity of that point cannot be non-zero, right? Unless it is some transient analysis, it will have to be zero, because that is by virtue of which we are connecting this. We are saying that this has no velocity. In such a case, if this is r, this has to be perpendicular. If this is r, this has to be perpendicular, is what we are trying to say. Uh, that I am not very sure. Let me check up on that and let you know. For this case, I am certain. Whereas for you are asking about cases which where this condition might fail. So there could be cases where it might fail or it might not. So that I don't want to comment without having analyzed and thought about it. In such a case, you if you allow me some time, I will think it over and I'll maybe answer you in the next session or maybe in the forum. I hope that is okay with you. Okay, yeah. All right. So we have got the velocity of point C as 1.12. So velocity of point C has come out to be 1.12. Now the question asks is 12 meters per second. Now next question is asking the absolute acceleration of point C in meters per second. Now this is a little involved. Now the thing is, we have identified that this is the ICR. This has non-zero velocity, but it does not have non-zero acceleration. Definitely has an acceleration pointing towards the center, which is centripetal. In such a case, it is better to do it by vector analysis. So in such a case, if I were to, let us say, acceleration of point C, this is the absolute acceleration of point C. If I attach a non-rotating translating axis at O prime, O dash or O prime, so this will be acceleration of O prime plus omega cross r c with respect to O plus alpha cross r c with respect to O. Now I know this is 0 in the question. In our case, it has come out to be 0. Now AC is nothing but, now I know that for a disk which is rotating, AO being the ICR, it will have a centripetal acceleration pointing towards the center of this curve. Towards the center of this curve. And its magnitude will be omega cross R. Which R? This will be the R, which is 0.25. So in such a case, I'll just write this as 2k minus 2k cross minus 2k cross will be minus 0.25 j. So this is the acceleration of the point of zero velocity. And then rest is straightforward. We have got this as 2k, sorry, minus 2k cross minus 2k cross. What will this RC with respect to O be? It is minus 0.5 I plus 0.25 j cap. Why? Because we go first like this. we go first like this, minus 0.5 and then like that. So this position vector is minus 0.5 I plus 0.25 k j. So this is what we need to solve now. So acceleration at c is nothing but, what will this come out to be? 2 squared into 0.25. So minus, so this will be 1 j, which I know it will point towards the positive j, so that is correct. Now I can take the cross product of these, which will come out to be 2 plus 2 I cap, and then it will be minus of minus 2 into 0.25. So this is minus 1 j. So I can see these two cancel out, and then acceleration of c is nothing but 2 I cap. So the magnitude is 2. Magnitude of the acceleration of point c, the absolute acceleration of point c is 2 meters per second square. Now the same we could have done by placing our axis here, in which case it will have only centripetal acceleration, which will be pointing, this being the center, it will be pointing towards that, which is nothing but 2. Omega is 2, so this will be 0.5. So omega squared r, which is 2. So I hope that that is clear. Yeah, yeah. No, because alpha is 0. Because alpha of that disk assembly is 0, that is why. Absolute velocity is objective. It is not with respect to something. It is with respect to any inertial frame of reference. See, we have calculated the absolute velocity, right? No matter where I look at this from, if I'm in an inertial frame, this is the velocity I will see. Yes. See, this disk assembly is having no angular acceleration, right? So any point we take, this center is having no acceleration. So if we have take this point, then it is almost like I have placed the fixed here, and then it is having only centripetal acceleration, which will come out to be 2 I cap. Instead, what I did is I put the axis here. Now, when I put my axis here, I also have to account for the acceleration of that point, which is what I had accounted for. That acceleration is with respect to fixed reference. Acceleration of O prime is with respect to O, which is having no acceleration with respect to fixed reference. So I either analyze point C from O, in which case I account for only centripetal acceleration. Another way is I analyze the acceleration of C from point O prime, in which case I need to account for the acceleration of O prime itself. That is what I have done. Both will give the same answer. Is it clear? Yeah, yeah, yeah. Okay. Yes, yes. Same. Yes. Why? Let us see that. In fact, let us see that. One was this line, this spoke, or which was rotating about its center. It is like that. Its center is here, so one was this line. Now the other is this line somewhere else. Now when I observe it from the fixed frame, let us say this is my, not to be confused with rolling. I'm just saying it is rotating, and this be the fixed, let this be the fixed frame. Let me put it here, not touch it. Okay. So in such a case, I draw my extension. This is my extended line. Okay. This is an extended line. So let this be some theta. at this moment. In the next moment, this line would have gone here. So now this will be my line joining the fixed reference, in which case now it has gone to some theta plus theta, theta plus delta theta. That delta theta by delta t is what is your angular velocity of this object. Same applies to this also. If I take my reference like that, and let us say this is my extended line. This is my extended line. After some time, it would have gone somewhere like that. Line would have gone somewhere like that. Now in such a case, what I do to extend it is, it is red. And then what I do to extend it is, I extend, it is going out of the plane of, out of the screen. But let us say I move it and then I reduce its size. Okay. So what will happen? This will be like that. And then this goes like that. It touches there. So initially this was my theta. Now this is theta plus delta theta by time t. These two will come out to be the same. The difference of these two will come out to be the same. So one rigid object can have only one angular velocity, only one angular acceleration. Now, what is the question? That why what was your doubt that that you were asking, that this is not holding? Okay. Okay. No, see, the thing is, the we are confining our attention here to one rigid object. So when we go to some other rigid object, how we perceive this can be different. This is, we are talking about only one rigid disk at the moment. So don't confuse with that. I hope that is clear. Yeah, yeah. Okay then. Very well. Okay, so in that case, we have finished this question. So let us try to look at this question now. A reel of rope with one end tied to a hinge, with one end tied to a hinge on the roof has angular motion as shown. So this is having both omega and alpha in this direction, omega being 4 and alpha being 6 in magnitude. We have been given one set of axes, x and y. So considering the positive coordinate axes as shown, compute the following quantities at the instant depicted. So the distance in meter of the instantaneous center of zero velocity of the reel from point A is what? Point A is over here. Now at the next instant, it would be something like that. It will go on moving down. So essentially, if we see, it is actually rolling about this point, in which case this is my instantaneous center of zero velocity. If I take it like that, so this is my instantaneous center of zero velocity. Now what is asked is, what is the distance in meter of the IC zero velocity from this point A? This distance is what is asked. Now let us represent it by a vector first for use in the other question. Let me call this point as O. I hope O is not used up anywhere, so as to not cause confusion. I can take that to be O comfortably. Okay. So this is A with respect to O. So with the positive coordinate axis, essentially I will be taking this axis and putting it there and then finding it out. What will that come out to be? It will be this radius of the radius of this reel is given to be 0.15. So it is minus 0.15 I minus 0.15 J. So this is my position vector. So the distance is nothing but the magnitude of this, which is nothing but 0.15 root 2. Since we have been asked in meter, we should make sure we convert this into meter. So it is 0.15 root 2, which is nothing but 0.212. which is also equal to R A with respect to O, the magnitude. Okay. Now the next it is asking the magnitude of absolute velocity of point A is, now we know that velocity of point A is velocity of point O plus omega of the real cross R of A with respect to O, when I am attaching a non-rotating translating axis to that. Now I know that velocity of O is 0 by virtue of that being the center of zero velocity. So this is nothing but, what is omega? I know from the question omega of the real, omega vector is nothing but 4 k cap. Because I cross j is k, it is rotating in that direction only. It is pointing out of the plane. Similarly, alpha is nothing but 6 k cap with consistent units in radians per second and radians per second squared. Okay, so this is nothing but 4 k cap crossed with this vector. Since the magnitude is asked, I may as well skip this and simply multiply it. But for the sake of habit building, because we have to do the same for acceleration also, in such a case, I want to go by this way. So I hope you can bear with me. So it is nothing but 0. Plus 0.6 I minus 0.6 j. Does that make sense? It will actually have a velocity 0.6 I minus 0.6 j. So it is having a velocity like that. Since it is rotating like that, omega cross r. So velocity will be like that. So this makes sense. 0.6 I minus 0.6 j. So the magnitude is 0.6 root 2. 0.6 is nothing but 0.848. The magnitude of this is 0.848 meters per second. Now the magnitude of absolute acceleration of point A is asked. So the absolute acceleration we know acceleration of A. If I were to do the same as fixing at ICR, then in that case A of O plus omega cross R A with respect to O plus alpha cross R A with respect to O. Only difference is that alpha is non-zero this time. So I know what is this AO. It is nothing but my 4K cross 4K cross 0.15 I, because this will be my vector. So omega squared R will actually give me a centripetal acceleration pointing that way. I'm just writing it in vector form. 0.15 I plus 4K cross 4K cross, this will be minus 0.15 I minus 0.15 J. And then I have 6 K cap crossed with this quantity because this is alpha. Alpha is non-zero in this question. So what will this come out to be? Acceleration of A is nothing but this will be, so this is minus 2.4 I, and then I have squared into minus 0.15. I have plus 2.4 I from the next quantity, and then I have 4 square into minus 0.15. So I'll have again plus 2.4 J, and then what will this give me? This will give me 6 into 0.15 plus 0.9 I minus 0.9 J. So this is after taking the cross products. I hope you are comfortable with cross products. If you are not, you can visit the lecture. It gives you one shortcut. When we are going for a double cross product, with the I, we just have to multiply these three terms and multiply it by minus 1. Similarly for J. When we go for a single cross product, this K cross J will give you negative. These two will give you the positive with flipped order. So if you practice some questions, you will get it easily. So this cancels out with this. So I have acceleration of A coming out as 0.9 I cap and 1.5 J cap. Now, does that make sense? Let us see analytically. Now, actually speaking, yeah, yes, without using the vector form, no, not necessary. Not necessary. See, if you put it here, then your alpha cross R will be like that. Centripetal will be like that. It is just the sum of these two. If this was your reference, it's the same. Centripetal will be like this, and then its acceleration is like that. So I have just added up those two vectors. It is up to you. Whatever is convenient to you, you can do. Not a problem. So if I were to take it with respect to my center, let us say, then this acceleration would have been 6 into 0.15, which is coming out to be 0.9. This is nothing but alpha cross R, where this is R. This is R, right? And the other quantity would have been pointing like that. Let me use the pink color just to highlight it. This would have been what? Omega squared R. Omega is 4. 4 squared into 0.15. So this would have been 2.4. But this point has acceleration. You must note that. So that is why it will have some give and take. So if you go by vector analysis, you will not have any issues as such. Is it clear? Yeah. Calculating which A? This A. Yeah, yeah. I'll explain it graphically so that it is much easier. So I have the disk like that. Not the disk, the reel. So this is my point A. Now I have this as my ICR. So this is having one acceleration like that. And when I look at this point with respect to that, it will be having an acceleration like that. Centripetal. And when I look at this again, because of non-zero alpha, it will also be having an acceleration like that. So this is that alpha cross R, where this is my R. If I take this to be my R, this is my R. Let me draw it in one more. See, this is my position vector. Okay. So this is R, C, sorry, A with respect to O. This is O, this is A. And this is having omega and alpha. This is acceleration of O itself, which is omega squared R1, where R1 is this. This is R1. So this is having that omega square R1. Then with respect to O, this is having a centripetal acceleration. This is omega squared R, A with respect to O. And this is alpha cross R A with respect to O. Because of this alpha. Because of this alpha, it will have an acceleration like that. So when we add up these three, we get, that is what I did vectorially. This was the first term, this was the second term, centripetal. Third term was this, the tangential term. And then we are correcting it for the acceleration of the origin itself, which we have taken. That is all there is. So if I add up these three vectors, I will get my acceleration. Okay, yeah. So that acceleration has come out to be 0.9 I plus 1.5 J. And the magnitude is asked. So I'll just take it 0.9 I plus 1.5 j. So this comes to 1.75. Now the angle that is made by this acceleration vector of A with the positive x-axis is asked. So let us go with this itself. So we had it like this. Let us say I took these two initially and I got my resultant like that. So it went here, centripetal plus alpha cross r went here. I got my resultant like that. And to this resultant, I added this. Finally, I got my final acceleration like that. And what was that final acceleration? It had two components. One component was 0.9 I and the other component was 1.5 J. So these were the two components. This is acceleration of C, absolute acceleration. So I can see this is actually the x-axis. So this angle is asked. So that angle is nothing but tan inverse of 1.5 by 0.9, which is nothing but 59 degrees. So it is nothing but 59 degrees, 59.04 degrees. Now it is interesting to see that if this acceleration, if in the absence of angular acceleration, in the absence of this accounting for centripetal, we would have had one acceleration like that and the other one like that. So it would have now what this is doing is the acceleration of O is pushing it like that. That is why it has increased its angle. I hope that that is clear. I have not confused you much. But anyway, that is just a side take. But the main aspect was this to be discussed, that this is nothing but 59.04 degrees. So I hope that this is clear. If you have any questions, you please feel to ask anyway. So in the meantime, I'll move on to the next question. Okay. At some instant, a pivoted massless disk of radius 0.3 meter. So we have a disk which has a radius of 0.3 meter, rotates with a constant angular speed of omega equal to 2 radians per second in the direction shown. So it is shown in the in the clockwise direction with our x and y given like that. So we'll continue with that. In the direction shown with two massless links connected as shown. So we have one link over here of length 0.4 meter. Then we have another link like that, which is making an angle 30 degrees with this point. And then this radius is 0.3. Neglecting any frictional effects, answer the following question. So what is asked? So magnitude of point C, magnitude of velocity of point C, acceleration of point C. So we need to find out magnitude acceleration of this point, Then angular velocity of the link BC, angular velocity omega of this link. Then angular acceleration of link BC, angular, all quantities we have to find. So we have been given alpha, we have been given omega for this disk, alpha we have been given as 0. For this we need to find alpha omega, for this we need to find alpha omega. Okay, so let us start with that. Now we know this distance is 0.3 meters. So naturally we can calculate magnitude of velocity of C. Velocity of C, the magnitude. Velocity of C magnitude is nothing but magnitude of omega of the disk into r of C with respect to its center O, which is nothing but 2 into 0.3, which comes out to be 0.6 meters per second. This is rotating with 2, right? So this omega is 2 minus 2 k cap actually. Okay, so we have the velocity of point C as 0.6 I and the magnitude will be 0.6 meters per second. So far, so good. The acceleration. Now we have been given that alpha is 0. So the acceleration can only be centripetal. So acceleration of c is nothing but omega squared r in this direction plus alpha cross r. Since alpha is 0, I don't even need to mention it. So this is nothing but 2 squared into 0.3, and this is 1.2 pointing in this direction. So acceleration of c in the vector form is minus 1.2 j cap. Okay. The angular velocity, the magnitude of angular velocity of link BC. So this link we have been asked. Now at this instant, we can see, if I were to remove this, at this instant, if I take this, just this part and paste it here, at this instant I can see its velocity is parallel like that. So this is 0.6, which is velocity of c, and we will have, by virtue of this being perpendicular, by virtue of this distance, this is perpendicular. So in such a case, this will have another velocity of b. And from the same concept that we discussed earlier, if I were to resolve this angle is same. Hence, velocity of b is same as velocity of c. So omega for the disk, therefore omega for BC is 0 at this instant. I hope that is clear. So there is no angular velocity. Yeah, yeah. Which one? Instantaneous? Yeah, yeah, exactly. We can do by that also. If we were to draw this, these two are parallel lines which meet at infinity. Yeah, that also, exactly. We can use that. So since these two are parallel, the lines perpendicular drawn meet at infinity. So there is no rotation essentially. So it can be done with instantaneous center of velocity also. That's a good point. Yeah. Yeah. Don't we know the direction of VB? We can't say. Exactly. We cannot say. So let us see that. Yeah, yeah. I think I didn't I skipped that part, I think. I'll just cover that. Not a problem. I understood your point. Okay, let this distance be some A, and let this distance be B. Now in the question it is given that for the instant depicted when the vertical distance between point A and point O is 1.2 meters. So I have my point A like that, and then I have my point O here. So this distance is given to be 1.2 meters. So if I take what is A? A is nothing but 1 sine 30, which is 0.5. And this distance B, we know the radius of the disk is 0.3. So this adds up. That is why this information was given. I think I skipped through in this thing. So that is what tells us that actually this angle is perpendicular. This angle is 90 degree. That is what tells us that this angle is 90 degree. Otherwise, there is no way for us to know. And if there is no way for us to gauge that angle, then what you said is absolutely right. We cannot draw VB like this. VB will be in some generic direction. in which case this might be having angular velocity. So because by virtue of this information being there, we know that this is at 90 degrees. Is it clear? Yeah, yeah. Yes, this is vertical, right? So that has to be parallel to that, perpendicular to that. Sorry. Okay, let me do it another way. Yeah, understood, no? Yeah. Otherwise, you can take this triangle and work out Pythagoras, which will hold, which implies that this is actually vertical. So if that is vertical, this is horizontal. Okay. So omega has come out to be 0. Omega of length BC has come out to be 0. The magnitude of angular velocity of link AB is asked now. This AB. This is omega AB, let us say, vector, which we can take it as omega AB k cap. For this, if we know BC, if we know VC, we know VB also. So since we know VB for the link like that, we know this is VB, which is equal to 0.6 I cap. And this is my point A. Let us say this is having omega AB, which is given by AB k cap. So this is my position vector. What is this 0.4? J, because it is pointing downward. In which case I can easily calculate omega AB as 0.6 by 0.4, which is 1.5 radians per second. I can do this by vector analysis also. Since I have been doing that for a number of cases, I'm just skipping that part. Anyway, I hope that that is clear. Now the magnitude of angular acceleration of link, both the links is asked. Since we know that its angular velocity is 0, that does not imply that angular acceleration is 0. From the figure, we can't make assessments about that. In such a case, we will have to go for vector analysis. So let us go ahead and do that. Okay, so this was point A, and then we have the link like that. This is point B, this is point A. Now I know this is having omega equal to 1.5 k. Alpha for this is alpha AB k cap, unknown at the moment. Then I have my point C like that. This is having, let us say it is having alpha as alpha BC k cap, and having no angular velocity. And then we know VB, velocity of C is nothing but 0.6 I. Acceleration of C is, how much was that? Minus 1.2 J. Very well. And we also know this point is having velocity of B is nothing but 0.6 I cap. Okay. So now we can see that acceleration of C is nothing but acceleration of B plus omega BC cross R, C with respect to B, plus alpha BC cross R, C with respect to B. Now clearly this is 0 since we have got this to be 0, so I'll just omit it out of the equation. Anyway, before I omit, let us say that acceleration of B I analyze using this axis now by attaching a non-rotating translating axis at A. So acceleration of B, I know it as acceleration of A plus omega AB r of B with respect to A plus alpha AB. Now let me just mark which quantities are 0. So this is 0. So that entire quantity goes to 0. I know A is a pin. So A is 0. So I know the expression for AB. I know the expression for AB. I know these two. Let me just take them here. Since this doesn't exist, I'll remove that. I'll put it here. Okay. This is 0. Now, if I know this, then my AC is this plus this quantity. So how many unknowns do I have here? And how many equations I can form from this? I have two coordinate axes, x and y. So I can have only two equations at best. So there better be only two unknowns. This do we know? Omega AB. We just found out. Omega AB was, we just found that out to be 1.5 k cap. So from here, this we know by virtue of that being connected to the disk. This quantity we know. These quantities we know. So only these two remain. So two equations and two unknowns that can be solved. So when I post this sheet, I'll solve it because I want to move to the other problems also to have a fruitful discussion. This is just a matter of substituting and executing the calculations and simple vector algebra. So that when I post the sheet, I will complete that and post so that if you are making an attempt, you can check it from there. I hope that that is okay. Okay. So let us look at, in fact, towards the end, if we find time, we'll revisit that. Yeah. So let us look at this question. The absolute distance of the instantaneous center of zero velocity in meter from the gear center is what? Is what is asked. So let us say that I take the mean radius like that, somewhere like that. So I have been given two velocities here. So one for this, since it is meshed, it is having a velocity of 1.5 meters per second. And the other, the bottom is having a velocity of 0.25 meters per second. Now, how to find the instantaneous center? Just draw perpendicular lines from here. So connect the tips and connect the tails. So this I can connect. The other one is that. So this I have got. So this is my instantaneous center. So I know, do I know this distance? The total distance is 5 meters. Since I have my radius at 2.5, so the total distance is 5 meters. So if I take this to be x, then this distance becomes 5 minus x. So from similar triangles, I can solve this. So 1.5 by x is nothing but 0.25 by 5 minus x. So if I were to solve this, so this comes out to be 4 point, x comes out to be 4.2857. So mind you, this is from the top. What we have been asked is the ICR distance from the center of the gear. So we just need to subtract out. If that distance is d, let us say this is the center. If this is the center, if this distance is d, d is nothing but x minus 2.5, which comes out to be 1.785 meters. So I hope this is clear. It's a simple problem only. Not only we can't say it isn't, that is what we have found, that it isn't. It is at a distance 5 minus x, where x is not 5. So it is a non-zero quantity. So it is not rolling about this point. Yeah, you can say that. Since this is having some velocity, so by virtue of this body being rigid, it can have only one omega, in which case it would have to be evaluated by these two velocities. So what is the question? Backward, yeah. Depends on what you are trying to analyze. What is your motive? What do you want to find in the problem? Okay, okay. Anyway, it will depend on what is your motive that you want to evaluate. You can do it that way. All right. Okay, so let us look at this problem. A slotted link is connected using a pin P. So we have this slotted link, and then we have a pin P which is connected to this disk. So we have the disk that rolls without slipping on the floor. So we have a disk that rolls without slipping, and we have a pin connected to that. This slotted link goes through that link. At the instant depicted, the angular velocity and angular acceleration of the disk are 1.5 and 1.75 and 1.5 respectively in the direction shown. So we have been given the directions. Based on the questions, answer the following. Based on what is given, answer the following questions. So what is asked? Velocity of p with respect to r denotes the velocity of pin p as perceived by an observer rotating with the slotted arm. Then what are its x and y components? So the magnitude of angular velocity of the slotted link, acceleration of pin P is what is asked. Okay, so let us see this. Let me add some pages here. So let us try to analyze this using what we saw earlier. Now I know that this is my ICR since that is rolling without slipping. This is point P, and then I have the slotted arm like that, and this is making an angle. This angle is 75 degrees, is what is said. So what is it that we know from the problem initially? So let us try to see that. Now if I take one triangle like that, if I take this triangle, I know this side is 1.1 meter, this is 118 degrees, this is 1.5 meter, this I don't know. For the purpose, let us call it x for the time being. So if I were to take it here, let me call this angle some beta. Let this angle be delta. So let us try to evaluate all the quantities first from here. Now I know from cosine rule, or rather sine rule itself I can apply. So from sine rule I know that x by sine 118 is nothing but 1.5 by sine delta, which is equal to by sine beta. This is from the sine rule. How many unknowns are there? I can club two at a time, so I have two equations. At best I can find only two unknowns from this. I have x, delta and beta as unknown. So I definitely need to evaluate something else. I can evaluate this when I know 1.1 and 1.5 and I know this angle. I can apply cosine rule and evaluate that. So x squared is nothing but 1.1 squared plus 1.5 squared, 2 into 1.1, 1.5 sine, sorry, cos 118 degrees. So from here, what does x come out to be? Cos 118. So this comes out to be 5 and then x squared. So x is nearly equal to root 5. So for avoiding decimals, I'll just take this to be root 5. All right. So now that we have found out x, we can plug it back in this and find out what is delta. So delta is nothing but sine inverse of 1.5 sine 118 by root 5. So delta comes out to be by root 5 sine inverse of this. So this comes out to be 36.32 degrees. Similarly, beta, I can just copy this. 1.1. Yeah. So beta comes out to be this 25.74 degrees. So we know these two angles and then we know the distance x. All right. So let us proceed. So we know this distance is root 5. This distance is root 5. And this angle, what is this angle? This is this beta plus 90 degree. This angle is beta. So we have beta plus 90. So beta is 25 plus 90. So this is 115.74 degrees. 115.74 degrees. Very well. Okay, so what does the question ask? If velocity, anyway, we have to get to that. So first let us try to look at this. Now from this figure, I can see that if this is my ICR, this is my position vector, then naturally my velocity will be like that. This is the absolute velocity of point P, of that pin P. So if I draw a line like that. Okay, now I can extend this line. So this is making an angle 75 degrees. Now from coincident point analysis, whatever we discussed earlier, we know that there will be a velocity which is along the slot shown in green, and then there will be another velocity which will be perpendicular. Actually, I shouldn't have drawn it that big. There will be one velocity like that, and then there will be another velocity like that, which will add up to the actual Vp. This is nothing but velocity of pin P as perceived by a person rotating with that with this slotted arm. What is that slotted arm's R? So this is R, velocity of P with respect to R. This is velocity of P, which is nothing but omega. This is omega of the slotted arm into R of P with respect to R. I hope this is clear. So we have discussed this in detail. So it is just a matter of finding out the angles now. I know what is this angle. It came out to 115.74. So this is 115.74. Now my focus is to find out this quantity. That is, I need to find out this and I need to find out that. For that, what can I do? I need this angle because Vp I know. What is Vp? It is nothing but omega of the disk into root 5, because this distance is root 5. So this is rotating about that. So it is just omega cross R. So omega of the disk is given to be, in the question, omega of the disk, since it is moving clockwise, it is 1.75 k cap, and alpha of the disk is given to be 1.5 plus 1.5 k cap. These quantities are given in the question itself. It is mentioned here. Okay, so omega disk is 1.75. So what does Vp come out to be? It is 1.75 root 5. It is 3.913 meters per second. Now, if I were to do it by geometry, since I did it by vector analysis and you had asked if we can do it by some other way. So I'll try to do this using just geometric this thing, at least the velocity part. So what is this angle? I know this 115.74. So this comes out to be 64. Yes, yes. Inst by instantaneous method, I have got VP. I'm just trying to find out what the other two are by coincident points, by having a fictitious point. Yeah. So this angle is 64, which means this angle is also 64.26. I know this is 90° because it is a cross product. It has to be perpendicular to the line joining the ICR. If this is 90, can I evaluate this angle? This angle will be 90 minus that. So this is 25.74. Very well. Now in the question, I have been given that this angle, which is same as this, is 75 degrees. So if I were to call this, let us say the angle of our interest, if I have to call it some other, maybe some phi. So from the figure, I can see that phi plus 25.74 is nothing but 75. So therefore, phi comes out to be 49.26. Now I have got phi. Now it is very straightforward, the analysis. So I have this angle as phi. I have this. So I can see that Vp with respect to r is nothing but Vp cos phi, and omega SARP is nothing but sin phi. So let us go ahead and do that. So from the figure, I can see that Vp with respect to r, vector's magnitude is nothing but Vp cos phi, and omega slotted arm into r t with respect to r is nothing but Vp sin phi. Now in the question, I know this distance. It is given. At the instant, this distance is 2.75 meters. So essentially, I know this. This is 2.75 meters. So V of P with respect to R is nothing but the magnitude is nothing but Vp. What is Vp? 3.913 cos of phi, which is 49.26. So therefore, velocity of P with respect to R magnitude is 2.55 meters per second. Now, what have we been asked? If Vpr denotes the velocity of pin P perceived by an observer rotating with a slotted disk, we have been asked in component form. So wherever we were asked in magnitude form, we did it using vector algebra. We got the components and then we took the magnitude. But here it is asked in component form. But since we have done it straight to get the magnitude, let us go ahead and make it into a vector. It is not a big task. I know that this is my unit vector in that direction. This is n cap. I know VPR is along n cap. So can I write what n cap is? I know this angle that it makes with the x is 75 degrees. So n cap is nothing but cos 75i plus sin 75j. So velocity of P with respect to r vector can be written as the magnitude into n cap. So we know both of them. Hence, we can write this. It will be nothing but velocity of p with respect to r is nothing but 2.55 into cos 75i plus sine 75j. So what is the x component of this? Cos 75. X component is 0.66 meters per second. And the y component is 2.643. 2.643 meters per second. So these are the two components. Now that we have answered this, okay. Next question is asking the magnitude of angular velocity of the slotted link. Now we can use this relation. We know this. I'll take it here, which gives me that omega of the slotted arm is nothing but Vp, which is 3. What was this? 3.913 cos phi. Phi is 49.26 divided by 2.75 meters. We saw this quantity was 2.75. So this will come out to be divided by 2.75. So this comes out to be 0.93. 2.913. Yeah. So this comes out to be 0.93. Magnitude of total acceleration of point P is asked. Now, for total acceleration, as you had also asked initially, that can be analyzed in two ways. Now, if I am constrained to rotate with this object, I can evaluate the absolute acceleration of point P. Only thing is, I will have to attach a rotating frame of reference to that, and then I have to account for the Coriolis force. Whereas from the absolute motion, from our normal relative motion analysis with non-rotating translating axis, if I attach the non-rotating translating axis here, I know this will have one centripetal acceleration, this will have one tangential acceleration, and then this point itself is having an acceleration towards the center by virtue of that being the ICR. So sum of these three will give you the acceleration. So that is all that needs to be done. Let me just write the equations for that. So acceleration of P. Acceleration of P I can take. Let me just call it ICR. Okay. So it is nothing but acceleration of ICR plus omega of the disk cross R of P with respect to ICR plus alpha of the disk cross R of P with respect to ICR. On the other hand, if I were to do it from that rotating frame of reference connected to the slotted arm, let me call it SL. Let me denote it by that. By the slotted arms analysis, it will be acceleration of R, which is the hinge, which is actually 0, but I'm just writing it in a full this thing, plus omega of the slotted arm cross R of P with respect to R plus alpha of the slotted arm cross R P with respect to R. But this will not be all. Since this is rotating and I'm having relative velocity, I will have Coriolis component. Slotted arm crossed with V relative plus A relative. So these two additions come in when I have my rotating frame of reference. What is VREL? VREL is what we calculated here. This is VREL because when I'm rotating with that slotted arm, this is the velocity I perceive. This is the relative velocity I perceive. So this is VREL. And then AREL I will have to calculate from vector analysis. So this will be the method to calculate the same acceleration of the same point, but with respect to rotating frame of reference. Whereas this is with a non-rotating translating axis attached to the ICR. There is another way to do it. Let us say that I take acceleration of point P as acceleration of the center of the disk. Center of the disk plus alpha disk cross R plus omega disk R. Now in this case, the R becomes the radius of the disk itself because we have attached to the center. However, this will not be non-zero. That is what we need to take care. This will not be non-zero because of the presence of alpha. So in these three ways, we can solve for absolute acceleration of P. When I upload the sheet, I will maybe solve it in all the three ways and upload it. Anyway, we have not looked much at this rotating frame of reference today because the more of the focus was on relative analysis using non-rotating translating axis. But the entire next week is dedicated on rotating frame of reference only and Coriolis effect and all that. So we will be seeing extensively how this is applied to problems in the coming next session. But for the sake of completeness, I will solve acceleration of point P by all the three methods and show that this is same. And when I'll upload this sheet, you can refer that sheet in order to find that out because we've anyway close to running out of time and I don't want to go on doing vector algebra. In that time, if there are any other questions, I'm happy to take them. So I hope that you can bear with me. Anything else, Mr. Steve? Yes, that VREL is this. P with respect to R. We are sitting at R. We are rotating with this slotted member. See, in this slotted member, wherever we sit, we are going to see VPR like that only. As long as we are rotating with it. Okay, yeah. Very well. So what we have seen today, I'll just brief through. So we saw that when we are rotating with the rigid body, we will not be in a position to calculate or rather correct for its Coriolis component of acceleration, which is a correction factor that we need to account when we rotate with an object and are actually perceiving relative velocity. If there is no relative velocity while you are rotating with the object, there is no rule of Coriolis in coming into the picture. So, and then we saw one relative motion question where we attached, and then we found 2-3 ways to go about solving for your velocity at the instant. If we can actually see that those two are parallel, by virtue of that being a rigid object, we can resolve those two velocities along the line joining those 2 points, and that would have to be the same in order to keep that body rigid. It cannot be violated, which gives us a constraint to actually solve for other things. Then in our coincident point analysis, we have seen that whichever point's velocity you can perceive while rotating with the object, wherever you see VREL to be 0, that is where you have the actual point, and the other member is where you fix the fictitious point or the coincident point as it is called. And how the coincident point comes about, how that analysis is done, we discussed that we draw two circular arcs at some time t. We know these two circular arcs will have velocities that are tangential to them. Then the third vector that connects it is what is VREL. So these two, we can write it in a vector form, and that is how we solve it. We are enforcing that F is in the circular arc, by which we can calculate omega of that slotted arm, because we are enforcing it to go along a circular path. The other one has to be relative in order to add up to the actual velocity of C. We have elaborate discussions on ICR and how to go about it. It is to be kept in mind that even though it is the center of zero velocity, its acceleration is not zero. Its acceleration will be pointing towards the center of this curve. So that is to be kept in mind and accounted for always. Other way to go about is that we fix it to the center, then we need not actually bother about calculating the acceleration unless that point doesn't have an acceleration. Other way to say this is that if the rolling object is not having any, if the rolling disk is not having any acceleration, angular acceleration, then the center's acceleration will be zero because its velocity is only linear. And we saw how two disks taking scribing line on two disks is tantamount to evaluating its velocity. So we are not constrained to have our lines parallel like spokes. It can be any line. In fact, this is what we thoroughly apply in our rigid body mechanics because not all objects are circular. Yeah, yeah, yeah. It will be twice that of VCM. Yeah, yes, you can see that because it's actually a triangle like this. So if this is confined within that disk, then naturally this becomes half of that. Whereas in our disk problem, that was not so. See here, it is not here. We know the velocity here. You understand? In this disk, we know the velocity here. So this is my triangle formed. Now, if I take half of that velocity and consider that to be the center of rolling, that will not be correct. It will always be this curve center. You take it like that. If there is just a single disk, then there is no confusion. This curve center coincides with that. Whereas if the assembly is like that, then if you draw a triangle like that, it is not necessary that whatever falls in midway is the center. That is not correct because we are extrapolating it to another dimension. We are supposed to account for this curve center only. I hope that is clear. Yeah. Yeah. Yes. Yes. As long as there is one rigid body, it can only have a unique alpha and unique omega, no matter where we see it from. Let us say we observe it from fixed frame and we have evaluated something. Then we go about in a non-inertial frame and evaluate something. That gives us a via media to link it and find the correction factor that we need to make. Because whatever is observed from the fixed frame is correct and it's universal and it can be only one value for one rigid object. I hope that is okay. That is clear. Yeah, yeah. Yes. Yeah. Yes. Yes. Force to one force and equivalent moment. Yes. 1 minute. Your voice is not coming out clearly. Can you just ask again? Yes. 1 minute. We have a beam. Ah, like that. Okay. Hmm. Moment or force? Ah, okay. Yes, yes, yes. Okay. Y center will be outside. Let me call this R. Let me call this also R. So this is R root 2. Now let us say this is my force that is applied. I need to have the same condition. What I will do is I will remove these. I'll bring this I'll bring this force here. Along with that, I will have to add one couple M. Yes, yes, yeah, yes. So couple is a free vector. You can place it anywhere. Let us say, let us say this was the case. Now what I did is I took this and I applied here. Okay. But I cannot just arbitrarily do that. So I also need to negate that effect. In negating that effect, I get a green. I just put an opposite force and I put it here. Okay. Now this green and that blue forms a couple. This green and this blue forms a couple like that. You are saying this is the center. But this couple is a free vector. I can place it anywhere. Why? Let us see like that. Let us see this is the distance. Let me see this is the force. This is F. This is also F. Let this be D. If I take, let the total distance be D. If I take moment about the center, what do I get? F D by 2 plus F D by 2 equal to F D 1. Now let me take moment about some other point. Let me call this X. Let me call this will be what? D minus X. Right? So if I take moment about that point, what will that come out to be? Fx plus F into D minus X. If I open this out, it is Fx plus Fd minus Fx, which is equal to Fd. What does this tell us? That it is irrelevant. Whatever point I take the moment, once there is a equal and opposite force separated by a distance d, I can put it anywhere and it will have the same effect. Yeah, that is what it is coming. In your case, if I take x to be d, it is the same thing. If I take x to be anything ranging between these two, it will come out to be the same. Mm, yes. And it is not necessary that I have to take my point inside this line. If I take it somewhere, if I take my point here and I take the moment like that, even that will come out to be the same. At any point in space, it will come out to be the same. No. So couple is that is why we call couple a free vector, meaning it can be pushed around. That is not same for force. Force is a sliding vector. It can only move along its line of action without altering the external effects. If it has to be moved to some other points, we have to counteract that by a couple. Yes. See, couple is a free vector, meaning once I have a couple, once let us say I have a beam and I have a couple. So no matter where I move this, it will still bring about the same external effect. You follow? But same will not be applicable for the bending moment. because bending moment and shear force are internal effects. Okay, this couple, if I place it here or if I place it here, my bending moment diagram will definitely change. But my reactions will not change. So this is M, let us say. So what will this is rotating like that. So I'll have my reactions formed like that to this beam. Okay, this will be M by L. This will also be M by L in the opposite direction. Now, no matter where I put this M in the beam, my reaction still remain the same because it is an external effect. Whereas if I were to move this point here, move this couple here or here or here and some other point, all my four cases bending moment diagram will be different. Bending moment diagram will have a jump at the point where the couple is applied because bending moment diagram is an internal effect. Sliding vectors connotation is with respect to external effects. Okay. Yes, that will be specified. Wherever the couple is placed, that is where we have to apply it in order to study the internal effects. Whereas external effects, meaning the reactions, we consider it by global equilibrium, considering it to be rigid body. That is how we calculate reactions, isn't it? Sigma m equal to 0. When we are doing that, we are considering it to be a rigid body, in which case external effects are not changing. So no matter where I move this couple, my reactions will be the same, but my bending moment diagram won't be. Yes. No. Yes. We need to know where it is. Yes. Different bending moment diagram. Yes, exactly. Okay. Yeah. Yeah. Okay. Well, anyway, we have run out of time. So I thank you for attending. So I hope that this was a fruitful session. So in the next week, we'll be discussing questions on rotating frames of reference in detail. So I'll see you next week then. Thank you. Thank you for attending. Yeah. Thanks.